It is part 3 of section 8.2, the K-Medoids algorithm, which is also called PAM algorithm, partitioning around the Medoids. PAM is similar to the K-means algorithm. They both are partitional. However, the K-Medoids chooses Medoids for cluster centers, and it can be with arbitrary distances. It's a little bit more flexible than the K-means algorithm in the measure, distance measures. And K-Medoids can be with error norm, for example. The PAM start from an initial set of Medoids and iteratively replace one of the Medoids with one of the non-Medoids points. And once it is improving the total distance, then keep going. The PAM works effectively for small data set, but does not scale well for large data set. And so computationally, quite expensive. So to reduce the computational complexity, CLARA, clustering large applications, and CLARANS, CLARA with randomized search, are developed. These two methods are based on samples. Okay, here we look at the original PAM, partitioning around the Medoids. Start with initialization. The K representative objects, they are Medoids, and associate each data point to the closest Medoid. So here now clusters will be formed. And now here, while the variance, the cost of the configuration decreases, we continue this iteration. For each Medoid M and for each non-Medoid data point O, swap and associate each data point to the closest Medoid. So here clusters will be formed, and for the formed clusters, we recompute the cost. Sum of distances of point to the Medoids, so that is basically the SSE. And the total cost of configuration increased, then we gonna undo the swap. That means just ignore the swap and computation. But if it is improving, so the cost decreased, then now we continue this here iteration. So swap and reform the clusters and recompute the cost. So once it's improved, then we continue this iteration. So it is quite expensive computationally. Okay, here, PAM is more robust than the K-means in the presence of noise and outliers. And the PAM works efficiently for small data set, but does not scale well for larger data sets. The runtime complexity of the PAM is given in this way for each iteration. And here, once the number of iterations is large, then it can be really expensive for larger data sets. So that CLARA, clustering large applications, are developed. That is a sampling-based method. So your PAM tried to find the best K-Medoids among a given data, and the CLARA finds the best K-Medoids among the selected samples. so that the samples don't include the original best the K-Medoids, then it can have some accuracy issue. Here we'll see some details around the CLARA and CLARANS. Okay, for CLARA, it's sampling-based PAM. It draws multiple samples of the data set and apply the PAM on each sample and gives the best clustering as the output. So make multiple samples, and then for each sample, PAM is applied. And here, after forming the clusters, and among them, best one will be returned. Here, the strength is it can deal with larger data set than the PAM. The PAM, the cost is increasing rapidly along with the number of points. Now, here, samples will have few points, so that even though you draw multiple samples, each one will take a much shorter time, so it's much more effective with a small the set, so that eventually here CLARA is more efficient than PAM. Okay, here weakness is efficiency depends on the sample size. If you try to choose a large sample size, then efficiency is not so much improved. And a good clustering based on samples will not necessarily represent a good clustering of the whole data set. That's really true. And here Medoids, particularly, the Medoids are chosen from the sample. So the algorithm cannot find the best solution if one of the best K-Medoids is not among the selected samples. So that means that it can be more efficient than PAM. However, it can be worse than PAM in accuracy. Here we have a CLARANS, randomized CLARA, and CLARANS draws sample of neighbors dynamically. Here CLARANS draws a sample of neighbors in each step of a search, while CLARA draws a sample of nodes at the beginning of search. So here dynamically and sample, and here now for searching a graph and finding a local minimum. Here we'll see a little bit more here. The clustering process can be presented as searching a graph where every node is a potential solution, and if a local optimum is found, the CLARANS starts with a new randomly selected node in search for a new local optimum. So here CLARANS draws a sample of neighbors in each step of a search and to find new local optimum and dynamically, so that the method will find several local minimums and several local minima and output the clustering with the best local minimum. It is more efficient and scalable than the PAM and the CLARA, and also can handle outliers. And by using some special techniques, it can further improve the performance. However, here it is also the weakness, yet the computational cost complexity of the Clarence is order n squared, where n is the number of objects, and the clustering quality depends on the sampling method. And again, this is a warning saying that Clarence may be worse than PAM in accuracy. And depending on the sampling method, the quality can be different. Okay, the PAM is good for small data, but for large data set is expensive, so that people try to use CLARA and CLARANS. But if your data is not so large, then try to use original PAM. It's better in accuracy. Okay, that's the end of the section. Thank you.